Welcome to this course on complex analysis. This is our first course on complex analysis. The prerequisites that will be needed for this course would be a sound understanding of basic linear algebra and basic real analysis. If you have seen some abstract algebra, that will certainly help. But other than the first lecture, the rest of the course will not use much material or much knowledge from abstract algebra. Regarding the textbooks, so let me note down a few books. So I should warn that we don't have a prescribed textbook for this course. However, most of the material that can be that will be covered in this course can be found in almost all the classical books written in complex analysis. However, I would like to refer the following books for this course. The first one being Complex Analysis by Stein and Shakachi. Stein and Shakachi. The second is titled Functions of One Complex Variable. There are two parts in this book, so I'll be the material that we will cover in this course will be found in the first part, and it's by John B. Conway. Of course, there are many beautiful books written in this subject. Maybe I should give a few other references. So there is this age-old classic. It's called Complex Analysis by Lars Alfors. There's also Complex Analysis by Theodore Gamlin. There's also this fantastic book, Real and Complex Analysis, with a slightly different approach. By Walter Rudin. Of course, there are many more books. Let me not write down all of them. And I would also suggest that you refer to these other references in maybe a second or a third reading. Okay, that's about textbooks. There will be weekly assignments in this course, and you are very strongly encouraged to work on these problems on your own. Should spend some time sitting and thinking about these problems. That will give you much better clarity on the subject material that will be covered. More or less everything to introduce the course to you. So let's now begin the study of the subject. In a course in real analysis, you would have started by studying rational numbers. You would have seen that rational numbers have certain deficiencies. For example, if you look at the Cauchy sequences, some Cauchy sequences in rational numbers, they do not converge. And real numbers were constructed precisely to address this particular problem. Real numbers were the complete field which contained rational numbers, and it was unique up to isomorphism, field isomorphisms. And you would have developed and studied an entire rich and beautiful theory of real analysis on this field of real numbers. But then, from an algebraic point of view, real numbers also have certain drawbacks. So there are polynomials, for example, which do not have roots in the real numbers. For example, x square plus 1 is a polynomial which does not have a root in the field of real numbers. Complex numbers was historically constructed in order to address this particular problem. So let's start this course by recalling what a field is. So a field F is a set with two operations. Let's call these operations addition, which I'll denote by plus, and multiplication, which is being denoted by cross, which satisfy the following properties. So these operations satisfy a set of properties. What are they? First one is mutativity. If you take two elements, x comma y in f, x plus y is always equal to y plus x. The order in which we take the sum doesn't matter, and x times y is equal to y times x. The order in which you multiply also doesn't matter, commutative. The second one is associativity. So for x, y, z in f, x plus y, if you add them first and then add it to z, this is going to be equal to x plus the sum of y and z. Which two elements you add first shouldn't affect the final result. Similarly, x times y times z is equal to x times y times z. Associativity is a property which holds for both addition and multiplication. The third property is existence of additive and multiplicative identities. Additive and multiplicative identities. There exists an element, let me call it 0, let me denote it by 0 in f, such that x plus 0 is equal to x for all x in f. This is the additive identity in f. There exists an element 1 in f such that x times 1 is equal to x for all x in f. So basically, there are two very special elements in the field f. What next? Fourth property is distributivity. The addition and the multiplication operations, they interact with each other. So for x, y, z in f, x times y plus z is always equal to xy plus xz. And finally, existence of inverses. So for x in capital F, there exists y in capital F such that x plus y gives you the additive inverse, additive identity. And for x in f minus 0, there exists a z in f such that x times z is equal to the multiplicative identity. So the multiplicative inverse is existing only for non-zero elements in the field f. So this is the set of all properties which needs to be satisfied by the two operations for our given set to be a field. So that's the definition of a field. And we are familiar with the field of real numbers. The set R is a field with the usual addition and multiplication operation. But the algebraic structure of the field of real numbers have certain drawbacks. So let me just note that down. However, the algebraic structure of R has certain deficiencies or drawbacks. For example, all polynomials need not have roots in the field of real numbers. So, for example, for every x in R, x square is positive, and hence x square plus 1 does not have, this polynomial does not have a root in R. And the complex numbers, the field of complex numbers is created or is constructed in order to address this particular drawback. Of addressing roots of polynomials. The field of complex numbers is constructed to address this drawback. Let me just start with a definition for a field of complex numbers. So, definition. A field of complex numbers C, this is a set, is a field. It's not just a set, it's a field which contains R as a subfield, which contains R as a subfield and a root I to the polynomial x square plus 1. The characterization is not over. Furthermore, this is not enough to speak about a field of complex numbers. We need something more. Furthermore, the field of complex numbers is the smallest such field which contains R and I. Rephrasing it, there does not exist a proper subfield of C containing R and I. When put differently, this says that C is generated by R and I. Or if you have C prime, a subfield of C which contains R and I, then C prime should necessarily be equal to C. So this is so let me just show you the definition of a field of complex numbers. So yeah, let me repeat the definition for you. A field of complex numbers is a field which contains R as a subfield, and also it has a solution to a root to the polynomial x square plus 1, and it is the smallest such field which contains both R and I. This is going to be our definition of a field of complex numbers. However, this definition immediately poses many questions. The first question would be, why would there exist such a field of complex numbers? And let's say we did manage to prove that there exists such a field of complex numbers. The second question would be, what if through another method we get hold of another field of complex numbers? Can we talk about any uniqueness? On which of these two fields do we study analysis on? So both these questions can be answered satisfactorily. So yeah, this definition, note what I just said, poses the following questions. The first one being, does there exist such a field of complex numbers? We might want it, but what is the guarantee that it exists? And the second one is, can we say anything about the uniqueness? So the rest of the lecture will be attempting to answer these two questions. Let's begin by addressing the existence. So in order to address the existence of such a field of complex numbers, we will be using some notions from abstract algebra, more precisely from ring theory. So if you have not seen a course on abstract algebra, there is no problem. You may skip the remaining part of the lectures. You can assume the existence and the uniqueness of such a field of complex numbers, move over to the next lecture. From the next lecture onwards, there will be more focus on the analysis on such a field of complex numbers. So we will not be needing too much of background in abstract algebra. However, in this lecture, we will be assuming some amount of knowledge in ring theory. All right, so let R of x be the collection of all polynomials, formal polynomials, over R, the field of real numbers. So formal polynomials, there is no need to make the distinction here, but nevertheless, let me make the right definitions. So these are, so a formal polynomial is an expression of the type a0 plus a1x plus ad x to the power d, where ai are real numbers and d is a non-negative integer, and d is a non-negative integer. Because this is a space which you would have seen many times and you will be very familiar with, but nevertheless, let me give a formal definition to make everything complete. So we will be familiar with the addition of polynomials, multiplication of polynomials. Let me not give all those things as definitions again. Let me just note that with the usual addition and multiplication of polynomials, R of x is a commutative ring with identity. With identity. So if you have not seen abstract algebra before, a commutative ring is set with two operations with almost all these properties satisfied except the last one. But anyway, so let me not focus too much on all those things. So R of x will turn out to be a commutative ring with identity. What are the the operations being? What are the identities here? The zero polynomial is the additive identity, and the constant polynomial 1 will be the additive multiplicative identity here. Okay, the first thing to note is that R of x is a commutative ring which is not a field. Not all elements can be inverted. In fact, any non-constant polynomial is not a unit, cannot be inverted. there does not exist a multiplicative inverse for any non-constant polynomial in R of x. Why is that the case? Because we have a notion of the degree of a polynomial, the d that appeared, and if you look at the product of two polynomials, the degree adds up. So if you want an inverse, we would, for a polynomial p, there should exist a q such that p of x times q of x is the constant polynomial 1. The constant polynomial 1 has degree 0. However, if p has degree greater than 0, then degree of px times qx will always be greater than or equal to 1, and hence it cannot ever be a constant polynomial. So let me just note that down. Since the degree of the product of two polynomials is equal to the sum of the degree of the polynomials, and the degree is always a non-negative number, and therefore non-constant polynomials can never have an inverse. Degree of the two polynomials. Alright, so this is a commutative ring which is not a field. Therefore, we can talk about ideals. So let's take the polynomial we are interested in. After all, why are we doing all these things? We are trying to get hold of a root for x square plus 1. So let's take the polynomial x square plus 1. Since x square plus 1, this is a non-constant polynomial, is not invertible, the ideal generated by x square plus 1 will not be the entire ring. The ideal generated by x square plus 1 is a non-trivial ideal. Recall that an ideal is a subset which is closed under addition, and if A is an element in the ideal, for any element B in the ring, A times B will be in the ideal. And the ideals are the right objects with which we take quotients in a ring. So what will happen if we take the quotient of R of x by the ideal generated by x square plus 1? We will be killing x square plus 1. That will be the right place to look for a root of x square plus 1. So let's define C to be the quotient of R of x by this ideal x square plus 1. What are the objects here? The objects here will be cosets of the ideal x square plus 1. And what will be the operations, that addition and multiplication we will have here? Let me write the operations down. So for the cosets, for p of x plus x square plus 1 in C and q of x plus x square plus 1 in C. So when are these two elements equal? Let me start from there. P of x plus x square plus 1 is equal, the coset representatives are equal if p of x minus q of x belongs to the ideal x square plus 1. This manifests in telling that i.e., so this is actually if and only if this is equivalent to x square plus 1 being a factor or dividing p of x minus q of x. So this is the equivalence relation of the cosets involved. And what are the operations, addition and multiplication operations here? P of x plus x square plus 1 plus, so we define addition in C, R of x mod x square plus 1. So the two such elements, two such cosets are added, the definition is basically p of x plus q of x, the coset represented by this polynomial. So this is the sum of two such cosets. And what about p of x plus x square plus 1 times q of x plus x square plus 1? This will be equal to, defined to be equal to p of x times q of x plus x square plus 1. These are the standard definition of the addition and multiplication operation which is being defined on the quotient spaces. And again, let me invoke the knowledge from ring theory to say that C is a commutative ring with identity with these operations. So we have found a commutative ring which is a candidate. So why is this a candidate? Okay, let's clear that first. Define the following map. Define, let's say, phi from R to C given by phi of A for any real number A. Define this to be equal to A, the coset represented by A, basically A plus x square plus 1. So it's a very easy check to see that this is a ring homomorphism, and also notice that phi is injective, phi embeds R into C. So claim phi embeds, phi is injective. To check it is injective, what do we have to do? So if, so proof of the claim. If phi of A is equal to phi of B, what does that mean? Then A plus the ideal generated by x square plus 1 is the same as B plus the ideal generated by x square plus 1. But that would mean that A minus B, or rather x square plus 1 divides A minus B. But A minus B is a real number. How can x square plus 1 divide A minus B? Any divisible, any factor, any multiple of x square plus 1 should have at least degree 2, or else it should be the 0 polynomial. So A minus B having degree 0, since degree of A minus B is equal to 0, we have A minus B is equal to x square plus 1 times 0, which is equal to 0. Whereas the degrees won't match, which implies A is equal to B. So immediately we see that the map phi from R to C is an embedding. It actually gives us a copy of R in the commutative ring C. So that's one aspect of the definition solved, and my claim is now that we can get hold of a root of x square plus 1 in this particular commutative ring. So let I be defined to be, so yeah, this is establishing the claim. So let I be defined to be equal to the coset represented by x square plus 1 in C. Recall that C is R of x mod x square plus 1. So you look at the coset represented by x. Then what is I square plus 1 in C? I square plus 1 will just be x plus x square plus 1 square plus 1 plus x square plus 1. This is what it means to look at I square plus 1 in C, right? This is equal to this. And by the definitions of multiplication and addition that we have defined in the quotient, this is going to be x square plus 1 plus the ideal generated by the coset represented by x square plus 1. But the coset of the ideal generated by x square plus 1, which is represented by x square plus 1, will be the 0 ideal itself, right? So this is just the 0 element of x square plus 1, because x square plus 1 belongs to our given ideal. And this implies that I square plus 1 is equal to the 0 in C. So hence we have both a solution to x square plus 1 is equal to 0 and a copy of R sitting inside. And a copy of, where was the map? Phi, let's see. A copy of phi sitting inside C. A copy of R sitting inside C. So we have addressed two of the aspects in the definition of a complex number, a field of complex number. In fact, we also can say about say something more about the characterization, namely that this is actually generated by R and I. How can we say that? Any element, you look at any element in C. So I am writing C. Remember that C is R of x mod x square plus 1. This is represented by P of x plus the ideal generator, some coset of x square plus 1, right? By some polynomial P of x. But then this also, this is equal to P of the coset representative of x, right? The polynomial expression of the coset representative of x. This is equal to P of I. That means IE, any element, coset representative of x is what we call as I, right? Any element of C can be written as a polynomial expression in of I with coefficients in R. But what can we say about any field of C which contains R and I? It will certainly have any polynomial expression in I, coefficients in R, because it's a field, because it's closed under both product and multiplication and addition. So this tells us that hence any subring of C which contains R and I should necessarily be equal to C. B, C. So we have, let's just go back to the definition of a field of complex numbers. This is our definition, right? Let me use green color to underline those aspects which we have already established. So this is a field of, it's a field which contains R. It's a field which contains R. This is something which we just established as a subfield. It contains R. Okay, as a subfield. As of now, it's just a subring, but we will come to that. And I is a root for the polynomial x square plus 1. That is also something which we have established. This is also something which we have just established. The only thing that is to be checked, okay, maybe I should, the only thing that is to be checked is whether it is a field. As of now, whatever we have constructed, see, it's just a commutative ring with identity. So if we establish that it is indeed a field as well, we would have proved the existence of such a field of complex numbers. So let's now work towards proving that this particular commutative ring is indeed a field. So in order to do that, let's focus on the polynomial x square plus 1 in R of x. The polynomial x square plus 1 is irreducible, is an irreducible element in the commutative ring R of x. So the first observation would be that an irreducible element in R of x would be prime. More specifically, x square plus 1 is hence a prime element. Recall what a prime element was. In a ring A, P is defined to be a prime element if whenever P divides AB, the product of two elements A and B in the ring, P either divides A or P divides B. That is the definition of a prime element. So the claim here is that x square plus 1 is a prime element in R of x. Let's just check that very quickly. Let x square plus 1 divide P of x times Q of x. Let's prove that it divides one of the two. So without loss of generality, if x square plus 1 divides P of x, then we are already through. If x square plus 1 does not divide P of x square plus 1 is an irreducible polynomial, and therefore square plus 1 is an irreducible polynomial, and therefore if you look at the greatest common divisor of x square plus 1 and P of x, it should necessarily be 1, right? So it will be a unit, so it will be 1 here. So let me phrase it this way: since x square plus 1 is irreducible, there exist polynomials alpha of x and beta of x such that alpha of x times x square plus 1 plus beta of x times p of x is equal to the constant polynomial 1. Now let's multiplying q of x to the equation above. We have alpha of x times x square plus 1 times q of x plus beta of x times p of x times q of x. This is equal to q of x. But if you focus on the left hand side, this term is divisible by q of x because there is anyway a q of x in this particular term, is divisible by x square plus 1 because x square plus 1 is anyway in the term itself. It's one of the factors. And here x square plus 1 divides the product p of x times q of x. That's how we began the argument. And therefore the left hand side is divisible by x square plus 1. Since LHS is divisible by x square plus 1, we have x square plus 1 divides q of x, and therefore x square plus 1 is a prime element, and therefore the ideal generated by x square plus 1 is going to be a prime ideal. And therefore we defined C to be the quotient of x square plus 1 by this particular prime ideal. We know that when we go modulo a prime ideal, we get an integral domain. Since x square plus 1 is a prime ideal, we have C is an integral domain. In fact, R of x being a Euclidean domain would have immediately told us that this is a maximal ideal, but let me not do that. Let me not give that argument. I would like to take a slightly more circuitous route to prove that C is indeed a field. So we just have established right now that it is a prime ideal and hence this is an integral domain. The fact that C is a field is now established only after showing that every non-zero element can be inverted. Okay, so let's set out to prove that. But before we get into that, notice that R of x is containing R is a subfield, right? Containing R inside. There is a copy of R sitting inside it. So notice that R of x, because R is there is a copy of R in R of x, this is a vector space over R. With generating set given by 1, x, x square, and so on. And since C is a quotient of R of x by an ideal, C is also a vector space over R. Well, we just checked that there is an embedding of R into C. It's a vector space over R, but the quotienting tells us where to look for a generating set. With generating set given by 1 I square and so on. But we know what happens to I in C. We know that I square is minus 1. And since I square is minus 1, we have 1 comma I is a spanning set of C. So we have a set consisting of two elements, which is a spanning set of C. Also notice that I does not belong to R. Why is that the case? Because if I belongs to R, what was I? I was the coset representative. I was the coset represented by the polynomial x. And if it is in R, that would mean that x plus the ideal generated by x square plus 1 is some a plus x square plus 1, where a is a real number, or that would mean that x minus a is in the ideal generated by x square plus 1, which cannot be the case because x minus a will have degree 1. Right, so I does not belong to R, and therefore 1 and I turn out to be linearly independent. So hence 1 comma I is a basis of C over R. So we have just established as a lemma, let me write it down. C is a two-dimensional vector space over R. We have still not proved that C is a field. So in order to do that, let's take an arbitrary element Z in C. So define mz, the map from C to itself, given by mz of w is defined to be z times w. We have already checked that C is an integral domain. This is left multiplication by z. And you should check that mz is actually an R linear map. It's a linear transformation. This is a linear transformation. This is an easy check. And you will immediately note that the null space of mz, what will be in the null space? It will be all those elements w, such that z times w is equal to the 0 element. But z times w equal to 0 is, in other words, telling us that, okay, so let me do one thing. Let me start with z, which is not the 0 element. So if z times w is equal to 0, that would mean that z is a 0 divisor, if z is a non-zero element, right? And C, we already checked, is an integral domain. Therefore, this cannot happen. So this is the only element in the null space of mz is necessarily the 0 element. No other element can be in the null space. And therefore, mz is an injective linear transformation from a two-dimensional vector space to itself. What can we say about an injective linear transformation from a finite dimensional vector space to itself? It should necessarily be surjective by the rank nullity theorem. So since mz is injective, or is an injective linear transformation, so linear operator from a finite dimensional vector space to itself by the rank nullity theorem, or the dimension theorem if you prefer it that way, mz is surjective. That means there exists some w prime such that z times w prime is the coset represented by 1. Hence, there exists W prime in C such that mz of W prime is equal to the unit element in C. And that means Z times W prime is equal to 1 and hence Z is immutable. Therefore, C is a field. So we have established every aspect of C being a field of complex numbers. Okay, so we now have one such field of complex numbers. We have answered one of the questions that arose from the definitions satisfactorily. Let's now move over to the second one. That's more easier than this, the question of uniqueness. Let me, in fact, write down a theorem directly to capture that. Let me write it down in the next page. Theorem. So, theorem. So, let C prime be a field of complex numbers with I prime a root of x square plus 1. Then C prime is isomorphic, field isomorphism to C. So any root of getting hold of a field of complex numbers you choose to take doesn't matter. You will eventually end up with an object, an algebraic object, which is isomorphic to the field of complex numbers which we have just constructed. But that's quite straightforward. Let's just quickly look at the proof. So let's define a map psi from C to C prime given by any expression, any element in C. We can think of the element as being a polynomial expression in I, right? So let's look at one such element. Let's take P of I and define it to be P of I prime. So notice that this particular map sends R to the copy of R, its identity on R, and it sends I to I prime. That's the map, and it will be a field homomorphism from C to C prime. So in particular, check that psi is a homomorphism. And because it's identity on R, it will be an embedding of C into C prime. Psi of C is a field, is a subfield of C prime, but this psi of C has certain characteristics which contains R. Because its identity on R, it will send R to R, right? It also contains I prime because psi of I is I prime by the very definition of psi. And what can we say about such a subfield? Because C is a, since C prime is a field of complex numbers, this forces psi of C to be the entire C prime, and hence psi is a field isomorphism. So we have established a remarkable aspect here. It tells us that with the definition of complex numbers that we gave here, the methodology with which we get hold of such a field of complex numbers, that really doesn't matter. However, we get hold of such a field of complex numbers which satisfies these properties, they should necessarily be isomorphic to each other. That is what we have just established. And therefore, we could study analysis over any one such field that we can construct. In the next lecture, we will get hold of another such construction of a field of complex numbers, and that will be more handy to work with, and we will be doing analysis on that field of complex numbers from now on. So as I had mentioned, this is one lecture which is very algebraic in its flavor. The rest of the lectures will slowly turn into being far more analytic. All right, let me stop here.